Welcome to the continuation of the lecture of the non-radiating dielectric guides. So, we will now look at the LSE odd mode, the explicit field expressions, and thereafter continue to the characteristic equations for the guide. So, for the LSE odd mode, we have in the dielectric region, which is mod x less than or equal to b by 2, E x as 0, E y is b d o j k z o prime sin q m o prime x cos n pi y by a e power minus j k z o prime z. E z is minus b d o n pi by a sin q m o prime x sin n pi y by a e power minus j k z naught prime z, or e power e to the power minus j k z o prime z. H x is b d o k naught square epsilon r minus q m o prime square by j omega mu sin q m o prime x cos n pi y by a e power minus j k z o prime z. Then H y will be minus b d o q m o prime n pi by j omega a mu cos q m o prime x sin n pi y by a e power minus j k z o prime z. H z is minus p d o k z o prime q o prime by omega mu cos q m o prime x cos n pi y by a e power minus j k z o prime z. Now, in the air region, which is mod x greater than b by 2, we have E x equal to 0, E y is j k z o prime b a o exponential minus p m o prime mod x minus p by 2 cos n pi y by a e power minus j k z o prime z, that is for x greater than or equal to b by 2 and that is equal to minus j k z o prime b a o exponential minus p m o prime mod x minus b by 2 cos n pi y by a e power minus j k z o prime z for x less than or equal to minus b by 2. Similarly, E z will be equal to minus b a o n pi by a exponential minus p m o prime mod x minus b by 2 sin n pi y by a e power minus j k z o prime z for x greater than or equal to b by 2 and that is equal to b a o n pi by a exponential minus p m o prime mod x minus b by 2 sin n pi y by a e power minus j k z o prime z for x less than or equal to minus b by 2. Now, h x will be b a o p PMO prime square plus k naught square by j omega mu exponential minus PMO prime mod x minus b by 2 cos n pi y by a e power minus j e power minus j k z o prime z. So, this should be O. For x greater than or equal to b by 2. And that is equal to minus BAO prime PMO prime square plus k naught square by j omega mu exponential minus PMO prime mod x minus b by 2 cos n pi y by a e power minus j k z o prime z, that is for x lesser than or equal to minus b by 2. Then h y is B A O P M O prime n pi by j omega a mu exponential minus P M O prime mod x minus b by 2 sin n pi y by a e power minus j k z o prime z. H z is B A O k z o prime P M O prime by omega mu exponential minus P M O prime mod x minus b by 2 cos n pi y by a e power minus j k z o prime z, that is for x greater than or equal to b by b by 2. And that is equal to minus B A O k z o prime P M O prime by omega mu exponential minus P M O prime mod x minus b by 2 cos n pi y by a e power minus j k 0 prime z that is for x lesser than or equal to minus b by 2. So, as before, equating the tangential electric fields at their dielectric interface, we will obtain the relationship between the coefficients in the dielectric and their regions. So, equating the tangential electric fields at the air dielectric interface we obtain BDO sin QMO prime B by 2 equal to BAO. So, following this, we write down the characteristic equations for the NRD modes. They are obtained by equating the tangential electric and magnetic fields at the air dielectric interface and using the Helmholtz equation in the dielectric and the air regions. So, please verify them from the previous given field expressions. So, equate the tangential electric and magnetic fields at the air dielectric interface and use the Helmholtz equations which will be written. So, that will give the yield the characteristic equation for the NRD modes. So, for the LSM even modes, we will get QME by epsilon r. So, 10 QME B by 2 minus root of epsilon r minus 1 k naught square minus q m e square equal to 0. So, this is obtained by equating the tangential electric and magnetic fields at the air dielectric interface. And now, the separation equation will be H square is epsilon r k naught square minus q m e square, that is equal to k naught square plus P m e square and k z e is given by root of h e square minus n pi by a whole square. So, if you want to find the cutoff frequency for the LSM even mode, we have to set k z e equal to 0, whence h e is equal to n pi by a. So, or h e square equal to n pi by a whole square, that will yield the relationship from this expression between k 0 square and q m e square. So, then we can replace q m e square in this equation by k 0 square and then find the cutoff frequency of the LSM even mode. So, then similarly for the LSM odd modes, we will have by the same methodology by equating the tangential electric and magnetic fields at the air dielectric interface, we will obtain q m o by epsilon r cot q m o b by 2 plus root of epsilon r minus 1 times k naught square minus q m o square equal to 0. So, this is the characteristic equation, and then the separation equation will be h o square equal to epsilon r k naught square minus q m o square, that is equal to k 0 square plus p m o square, and k z o, the propagation constant along the z direction for the LSM odd mode, will be given by root of h o square minus n pi by a whole square. So, again to find the cutoff frequency of the mode, we set k z o equal to 0. That condition is going to yield the cutoff frequency of the LSM odd mode. For the LSE even modes, we have q m e prime tan q m e prime b by 2 minus square root of epsilon r minus 1 k naught square minus q m e prime square is 0 with h e prime square equal to epsilon r k naught square minus q m e prime square, that is equal to k naught square plus p m e prime square, and the propagation constant along the z direction for the LSE even mode given by k z e prime as h e prime square minus n pi by a whole square. So, similarly, if you set k z e prime equal to 0, we will obtain the cutoff frequency for the LSE even mode. Now, for the LSE odd modes, we have Q M O prime cot Q M O prime B by 2 plus square root of epsilon r minus 1 k naught square minus Q M O prime square equal to 0 as the characteristic equation. Along with the separation equation, H O prime square equal to epsilon r k 0 square minus Q M O prime square, that is equal to k naught square plus P M O prime square, and the propagation constant along the z direction for the LSE odd mode k z O prime being given by root of H naught prime square minus n pi by a whole square. Okay. So, this completes our treatment of the NRD guide, including the field expressions and the characteristic equations for the modes, together with the cutoff conditions for the hybrid modes of the NRD. So, thank you.